Hello and welcome. This is SFU Math 152, Calculus 2. My name is Brenda Davison. We are now section 9.3, Separable Equations. So this is going to be the one method that we learn in Calculus 2 of how to solve a differential equation, a specific type of differential equation. The equation is going to need to be separable for us to be able to solve it, and we can solve the separable ones by integrating. There's lots of other techniques for solving differential equations, but those are not going to be discussed here, just this type here. So that is the reason for this word here in the title. It refers to the type of differential equation. Okay, first let's just review over a few things. One is we have a differential equation here that we're going to solve, but what we want to take a look at here is the slope field. Also, we call this a direction field, and we want to make sure that we understand how this thing comes about. So let's just take a one of these dashes on the slope field, like say this one right here. Okay, that one right there, the slope, that line, that is a small line which has a slope. And as you recall from Calculus 1, the derivative is the slope. So dy by dx for some function y equals f of x at a point, dy by dx at a particular point is the slope. So this would be evaluated at some value x equals a, and that will be equal to the slope at x equals a. Okay, so we have a point here. We have a point, I've indicated that point here is 1.5. And we can actually calculate dy by dx. This is how we make the direction field. We don't have to solve the differential equation and take a derivative. We already know what the derivative is. We got told dy by dx is square root xy, and that is square root 1 times 0.5, and that is 1 over the square root of 2, and that is approximately 0.707. So this line right here, then, this one that was drawn here, is drawn with slope of this line. So that is how these things are found out. Slope of this line is 0.707. Okay, so we don't know the function, not yet, but we do know what the derivative of the function is because we have a differential equation. We use that derivative information to figure out the slope at lots of different points. And I mean, this slope here at 0.707 only applies at the point 1, 0.5. So we just draw a little tiny line saying the solution curve will come tangent. This will be the tangent line to the solution curve at this point. So that is what allows us to visualize what the solution may look like. Okay, a separable equation is a special type of differential equation. It's first order, and it is a type where you can factor the derivative into a product of two functions in the such that one function is just of x and the other function is solely of y. Okay, so in Calculus 1, we saw one differential equation. So Math 150 or 151, we had one differential equation. I'm always going to be abbreviating differential equation like this, DE. We saw one differential equation. It was this one, y prime equals ky. And we were told that the solution was y equals a to the kt. And we simply did not know how to do that, but we were able to check the solution and say, okay, however you managed to come up with that function, it is the correct function. So that is the one thing we knew from Calculus 1. Let me just make another note. Most differential equations are difficult to solve. There's particularly the partial differential equations. So there's two types. There's ordinary differential equations where we have the regular derivatives we're used to, and what you're going to see coming in Calculus 3 is a partial differential equation. Don't worry if you don't know what that means, but particularly these ones are difficult to solve. But anyways, they both can be difficult to solve. And what we're doing now in Math 152 is we're expanding from 1. This is very exciting. Think about it, Math 152, expand from one differential equation to a whole class of d's first order separable. We'll be able to solve all of this type. So we're getting a bigger hammer. Bigger hammers are better. Okay, all right, so here's back to that original problem. There's our slope field reprinted there, and we have it this time an initial condition, and our initial condition is y at 0 equals 1. So we go to where x equals 0 and where y equals 1, and that's this point right here. And that then allows us to sketch this solution curve. So this is, I mean, this is, the y is down there, but this is y versus x, and this is the solution curve. So whatever function we find this to be, it will look like this black line. Okay, and the initial condition allows us to choose that particular solution curve in and amongst the family of solutions that we could see here on the slope field. So for example, had our initial condition been here, we would sort of go to trying to best we can follow the slope field, and we would have this curve. That would be our solution curve if our initial condition here was a y of 0 equals, where did I draw that? Looks to be about 0.2. Okay, then we would have that solution. So there's a family of solution curves. The initial condition allows us to pick which one it is, and the direction field allows us to get a visual representation of the solution. Okay, now let us do the highly exciting thing and see how we can solve this separable differential equation. Now I'm going to say it sort of colloquially here. When we want to do these separable things, what we want to do is put everything to do with y on one side and everything to do with x on the other side. It'd be slightly more formal here. We can see that we could write this like this. Whoops, I have to do it in a different order. Square root x, square root y. Could write it like that, which, as you can see then, is some function of x multiplied by some other function. Well, in this case, it's the same function, but it could be a different function of y. Okay, so it's separable. So that means we'll be able to move everything to do with x to one side and everything to do with y to the other side. I will, by convention, put everything to do with y on the left and everything to do with x on the right. It doesn't have to be that way, of course. Do it either way. But okay, so now I can, everything to do with y over here on the left, everything to do with x over here on the right. Okay, so that's separating it and writing it in terms of differentials. Then step 2, integrate both sides. Don't forget the constant. So let us go ahead and do that. Integrate both sides. And we will not forget to put the constant here. So this is going to be 2 root y when I integrate. We only need one constant. And because think about it, if we had two constants, we could just, if I had to put another constant over here, I could just move it and combine it with this constant into some other different constant. So we just need one constant. Okay, so then I could maybe just rewrite this like this. Square root of y is equal to x to the 3/2 over 3 plus some constant. I mean, it's not going to be the exact same constant as above. Sometimes you'll see me just using the same letter because it doesn't matter. It's just to indicate there's a constant there, and I'm going to fix that with the initial condition, and I just kind of carry through the same letter, even though I might be doing some algebra, which would mean that you know, C is not equal to D. But sometimes you will see me go like this, and it's I mean, this C in some sense is half of this one. It is, but it doesn't matter until the end. So sometimes I'll kind of be a bit lazy and do that and just use the same letter throughout, and it may actually be changing. For now, let's just do it this way. Okay, now we have an initial condition. We know that when x is 0, that y equals 1. So we put that information into our solution, and we find out that we get the square root of 1 is equal to 0 to the 3/2 over 3 plus d, and that means that d is equal to 1. So now we can write out the complete solution for our differential equation. It looks like this. It's actually not just a solution to the differential equation. This is the solution to the initial value problem. The initial value problem was a combination of the differential equation and the initial condition. Okay, so now here we have the same equation, the same differential equation, and what's different is this here. This is a different initial condition. So just like I showed you before, can you redraw this one here that we had from before? That was a point, it was at here. So we had earlier, we had this, oops, let's get that a little bit, try to stick with the lines the way they're going. So this was the last problem that we did, part A. And now we have a different curve. The solution to the differential equation is the same. The only thing that's different is the initial condition. So we already know from before that the square root of y is equal to x to the 3/2 over 3 plus a constant. And now we have a new initial condition. When x equals 2, y is equal to 2. So we simply plug that in. Square root of 2 equals 2 to the 3/2 divided by 3 plus the constant. And we solve for the constant, and we find out the constant is now, in this time, is now equal to root 2 over 3. So that then allows us to write the full solution to this initial value problem in this manner here. Okay, and if I wanted to, I could, of course, write by squaring both sides. This is a sort of an OR situation. This is just an algebra thing. There we go. Okay, so that is the solution to this initial value problem. Next example, find a general solution. I think we have the direction field for this coming as well. Yeah, we do. Okay, so we're going to find the general solution to this, and then we'll look at the direction field and see where we would have a solution curve depending on potentially getting an initial condition. Right now we do not have an initial condition. We simply have a differential equation. That means we're going to find the general solution, and that will include one constant. And that constant will not be we will not be able to determine that constant until we get an initial condition. All right, so first we look, does it appear to be separable? It looks like it's separable. They're always going to be separable in this course. And so we put everything to do with y on one side, everything to do with x on the other side. More formally, we write the equation again using differentials, and that looks like this. Okay, there we go. We integrate both sides. See why we do that, and we sort of do this topic in this course because we've just learned how to integrate. We understand what the indefinite integral means, and that allows us to use that in this application of solving differential equations, which are enormously important in science, in physics, and chemistry, and biology, and in psychology, and they're everywhere. You cannot escape from the differential equation. Okay, here, so then we do the integration. We get 2 square root y minus 1 on the left, and we get x squared plus c on the right. And then I'm going to solve for y. And I will end up with the solution written y equals f of x in this manner here, x squared over 2 plus some constant squared plus 1. And that is our general solution. So that is the general solution. Okay, there is the direction field for the differential equation that we just solved. So we have a direction field here. And now if we were to be given some sort of an initial condition, let me just say that if we were given an initial condition, say right here, like that, so this would be initial condition. It doesn't have to be at 0 either. I mean, we could be given an initial condition right here. Anywhere we can be given an initial condition. Often we sort of consider the time like this. Sometimes this is, I mean, right now it's an x-axis, but this sometimes is time, is And then that we often then say, well, when the clock starts, we know something, and that is why it's often that the initial condition is at 0. Okay, should that be the case, we have this initial condition, then we can sort of follow along the direction field lines and observe that, getting a bit steep there, observe that there we go, something like that. That's what the solution curve would look like with that initial condition that I just randomly picked. Clearly, if you make some other initial condition somewhere over here, then you would begin to follow. It's coming down very steeply. You'd begin to follow these things down here like this, and then we've actually don't have any information yet here. We would have to fill that in, but we would do that the same as before, and then we would have the solution curve for this initial condition. Okay, let's do another one. And so you need a few examples of this, and it's not, I don't think this is really a particularly complicated idea once you see it in action, and then because we already have spent quite a bit of time learning how to integrate. Okay, we'll do another example, and we have the direction field for this one as well. Computers are awesome for drawing direction fields. This is a routine calculation. It's algorithmic, so don't feel shy when you're trying to figure things out. Just go to something like Wolfram Alpha or whatever other software you use, and just enter slope field, and then enter the differential equation, or enter direction field and enter the differential equation, and have a look at what's happening. It's a really powerful tool. Okay, so everything to do with y on one side, everything to do with x on the other side. Maybe I will do it in red. Do it in blue. Okay, dy 1 plus y squared over y, and that's going to be equal to the cosine of x dx. Okay, and then I'm going to integrate both sides. And before I do that, I'm going to rearrange the left side a little bit. I'll write it like this, 1 over y plus y dy equals the integral of cosine x dx. So I just divide that y into both pieces in the numerator. That makes it easier for me to integrate. So now I can integrate, and I'm going to get the log, the absolute value of y, plus 1/2 y squared is equal to sine x plus a constant. Okay, now in this case, I cannot solve for y. I cannot solve for y and write y equals f of some function of x explicitly. That's no trouble. Okay, when we can't do that, that's fine. We can still compute y if we're given a value of x. We may have to do it numerically, but we can still compute it, and we can still this still is a general solution. Okay, so we have we recall this then is an implicitly. So we did implicit differentiation in Calculus 1, and this you will recognize as an implicitly defined function. Okay, y is still a function of x. Now the function is implicitly defined, and then we see a direction field that we can plot out, and we would, if we were to get some initial condition. So let me say here, this is the direction field for all possible initial conditions, and I may then choose an initial condition. Let me just choose one right here. There. Imagine that's my initial condition, whatever that is. X of, looks like about minus 3.5 equals whatever that number is there. It looks like it'd be about minus 1.5. Okay, so I get an initial condition like that, and then I can draw the solution curve by following along the arrows, doing what the arrows tell me. The arrows are telling me time to decrease, 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 and increase, 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 like that. And you know, when I see a curve like this, I'm looking at my solution as well, and I see this here. So I'm not actually particularly surprised to see somewhat periodic behavior. So that makes me kind of feel happy. I get some feedback that things might be going well. Always be on the lookout for clues that things are going well, or possibly more importantly, for things that are not going well, that you can then think, maybe I better revisit that and check. Okay, let's try another example. Find the equation of a curve that passes through the point 1, 1 and whose slope at xy is y squared over x cubed. This is only a slightly disguised version of exactly what we've been doing. Okay, so what are we being told? We are being told, find the equation of a curve. Okay, so we want to find the equation of a curve. We're being asked for sort of y equals fx. It may not even be a function, but it'll be some equation of a curve. So we're looking for something with x's and y's in it with an equal sign. And we're supposed to pass through the point 1, 1. Well, that means that y of 1 equals 1. And we get told the slope at xy, so a slope at an arbitrary xy value is y squared over x cubed. That means that dy by dx is equal to y squared over x cubed. Okay. So now we have these two things. We see that this is basically just a statement of an initial value problem, and that we can go ahead and solve it just like we have on the previous examples. Everything to do with y on one side, that's dy by y squared, and then everything to do with x on the other side, dx by x cubed. Integrate both sides. Find out that that means minus y to the minus 1 is equal to minus 1/2 x to the minus 2 plus a constant. And then maybe do a little bit of algebra, get rid of the minus sign by multiplying through by minus 1. Take a look at it this way. 1 over y is 1 over 2x squared plus d, like that. And then we have the initial condition. We know that x equals 1 means that y equals 1. So we can plug in 1 for y and 1 for x. Let's do that. 1 for x. And then find out that d is 1/2. Okay, so now we have a solution that looks like this to the initial value problem that we were given in words. It looks like this. Okay, and then maybe we want to write that slightly nicer. We could do a little bit of algebra and write it like this. Okay. And then we have a direction field, and we could see that depending on our initial value, we get actually quite different behavior. So for example, if we had an initial value here, we would find that the solution would sort of plunge off to minus infinity. We find that if we were to be getting an initial value, for example, here, we find that after when x gets large, that we would be, looks like we would be possibly reaching some sort of asymptote over here. Okay, so we can see that depending on your initial condition, you might end up in a wildly different finishing spot. And in this case, you're headed this direction, and in this case, you're headed in that direction. It's remarkably different. And then, of course, you could see if you're starting above the x-axis, that you're going to have, like say we had an initial condition, I don't know, right here, then we would see that you're going to kind of come down like this, and then it's a bit confusing with the direction field here, but you could expand it and or look at the analytical solution, and you'll see that it's going to come something like that. Okay, so then we have that kind of behavior. Very different behavior depending on the initial condition. I guess maybe the final thing I want to say about the initial condition, imagine this is a situation where we've got, you're modeling the ocean waves, and you're saying you're going to have a differential equation that models the ocean wave flow, and you're going to solve that differential equation, and what it's going to be telling you is the position of a dropped object over time. So you imagine dropping an object into the ocean, and then you want a function that you want to find a function that tells you where is that object at any time t after you've dropped it into the ocean. Let's just say you drop a little cork into the ocean, and you want to know where is it 2 days later, 2 weeks later, 5 months later, like that, and you have some sort of a model of the ocean current flow, maybe even including wind action. Anyways, you have some system that you solve to give you a function to predict the position of that cork as time goes by. Now, where you drop the cork in the ocean is the initial condition, right? So you have some, let's say you have Europe and Africa over here, and you have North and South America over here. You have the Atlantic Ocean, spell that correctly, and you drop your cork, and you've got a model, and say that's your initial condition. You drop your cork here. I mean, from the way I've drawn it, we don't actually know, but it would look like what would happen over time is your cork would basically move over here and land somewhere in the Americas, right? Whereas perhaps if you drop the cork here, it would maneuver over and land somewhere on the European shoreline or possibly in Africa. Okay, now there's going to be somewhere here where actually it's going to be like this cork would go that way, and then a cork dropped a very similar location, but just a little bit differently, is going to go this way, right? So sometimes a long-term solution, or what happens, is extremely sensitive to the initial condition. We're kind of seeing something like that here. If, for example, we were to get an initial condition, it's a little bit hard to tell from this direction field, but just to try to make my point here, if we were to get an initial condition somewhere here, it looking like we may well just come along here like that and kind of bloop there and then go like that. Whereas if we were just a little bit over here, rather than doing that, we're going to go like that. It's the same kind of idea. So sometimes a physical process, I mean, one differential equation, the long range behavior, which often you're very interested in, depends very dramatically on a small change in the initial condition. Okay, here we go. Final topic for this lecture is an orthogonal trajectory. So an orthogonal trajectory of a given family of curves is a curve that intersects each member of the given curves at right angles. Okay, so here it is a family of curves. These are hyperbolas, and they're plotted below here for a variety of values of k. So here, this equation here looks like this. This is a function, and well, it's an equation actually, and we've got here y versus x, and this line right here is what would happen if k were to be equal to 0. That means x squared would be equal to y. That means y squared, and that means x would be equal to y, and that's the line x equals y. Okay, and then so here, this line here is if we put k equal to 1, etc. So we can change the values of k here, and then we can plot those curves. No differential equation here yet at all. Okay, so there is a family of curves. They are hyperbolas. So the blue line are, let me just write this down so we're clear. The blue lines below, blue lines equal this curve, for a variety of values of k. Okay, so that's why we call it a family of curves, because we're not, k is a parameter, and we're just changing the parameter and replotting the curve. You should ask yourself right now, and maybe if you can't say it clearly, to talk to a classmate or talk to me during the Zoom lecture, what is the difference between a variable and a parameter? Because there is a difference, and you should make that clear to yourself. In this equation here, k is a parameter. Okay, next piece of vocabulary, we are asked for an orthogonal trajectory. What does that mean? It means some curve that passes through all of these curves and always at a right angle. So let me try to draw an orthogonal trajectory. It looks roughly like this. Okay, sort of wobbling happening here. It's not supposed to wobble. Okay, and the point is that each one of these intersection points here is a right angle. Okay, so that always this line here is the orthogonal trajectory, and it is always at right angles to any one of the blue curves that I may draw. And what we want to know is what is the equation of that line that I just drew, that red line. I mean, it's over here too. It's not just, it's there like that, and in fact it's here like this. So it's always all these right angles here. So these are always at right angles like that. Okay, all four sides. So this, I mean, I think at initial blush, this looks like a pretty hard problem. But let's just think about what we know about slopes, and particularly because we're in a lecture where we're talking about differential equations. So I think a really key point into solving this is that orthogonal means product of the slopes is -1. Okay, so the product of the slope, like if I just was to look at that point right there, the product of the slope of the blue line and the slope of the red line is -1. Okay, so the next thing we're going to do to solve this problem is take a look. We start here. We have this x squared minus y squared is equal to k. And then I can say, okay, I want to know that I'm going for this product of the slopes is -1. So then I'm asking, what is the slope? What is the slope at xy for this equation? Okay. And so how do I find a slope? Well, I take a derivative. And in this case, I'm going to take the derivative implicitly with respect to x. So I'm taking this, differentiating with respect to x. And then I'm going to solve for y prime. Y prime is dy by dx. So I find that dy by dx is equal to x over y. So that is the slope at xy for that family of blue hyperbolas. Now, I want to know what the equation of the orthogonal trajectory is. That is the red line. So now I know, so this was sort of step one. Step two is then I now know the slope of the orthogonal is dy by dx equals minus y over x because xy times minus y over x is -1. Okay, it's a negative reciprocal. So good news, really now my problem is solved because I'm now managed to translate what looks new and perhaps difficult at the outset. A little bit of thinking about what we already know. What we already know is at some point in our careers we've known this, and all we're doing is applying that, and then we are getting a differential equation that describes the red line. Then all we have to do is solve that. So now I'm going to solve that differential equation that describes the red line. And I solved that by separating. So it's minus dy over y equals dx over x. I integrate both sides. And then I find out that, why don't you do this as an exercise to confirm, but I find out that log of xy is equal to D. So this is the family of red curves that I've drawn on here. So the equation of these guys here is log xy equals D for a variety of different values of D. Then I can get them all. So this so I can find what those orthogonal trajectories are. I find this kind of an interesting problem. Okay, the next kind of problem that we can solve now is a mixing problem. These, in my experience, I have found students sometimes find difficult. So I'm going to go through it slowly, setting it up. After we get the differential equation, no problems. We can go quickly from there. But let's take a little bit of time setting it up. And you may, in fact, want to stop the video right now and spend 10 or 15 minutes trying to solve this yourself and seeing how well it goes and checking it. And if something is not working for you, then when you see the video, you'll realize, oh, that's what I didn't see, and that'll make it easier for you to learn how to do these things. Okay, so what we're going to do is let y of t be equal to the amount of salt in the tank at time t. So we've got this tank filled with pure water, and two different concentrations of salt are pouring in, or not pouring in, not concentrations of salty water are coming in. We're assuming it mixes just instantly and really well, and then a salty water is draining out, and we want to know how much salt is in the tank after some amount of time, after t minutes. Okay, so I mean part B is kind of silly in some sense, because if we know part A, we can calculate it at any time that we want. So we're going to we have a question. How much salt is in the tank? See the question? How much salt is in the tank? So I immediately turn around and say, okay, then fine, I'm going to need to know that. So, and it's going to be a function of time, so I let y of t equal the amount of salt in the tank at time t. Okay, and then I consider, what does dy by dt mean? Dy by dt is the rate of change of salt in the tank, right? Because that's what a derivative is, the rate of change. So dy by dt is the rate of change of salt in the tank. And that will be equal to the rate of addition of salt minus the rate of removal of salt. The next thing I'm looking at, a tank contains 1,000 liters of pure water. That's at the beginning. That means there's no salt in the tank. It's pure water. So from that, I understand that y of 0 is 0. Okay, then I'm going to consider, I've got now I've got something written down here. I've got the start of a differential equation here, and I've got an initial condition. And then so what I clearly need to figure out is these two things here. What is the rate of addition of salt, and what is the rate of removal of salt? So let's tackle the first one first, rate of addition. Okay, we have brine that contains, so brine, again, if you don't know the meaning of any words, brine not maybe being as common of a word that we normally use, then you should look it up. But brine means salty water. Okay, so salty water that contains 0.05 kilograms of salt per liter. I'm going to actually do this in a color so we can see what I'm doing. So I'm at the rate of addition, and I'm looking at what's coming in. Brine that contains 0.05 kilograms of salt per liter enters the tank at a rate of 5 liters per minute. Okay, so let me just get that part down first. How much salt is coming in? 0.05 kilograms per liter times multiplied by 5 liters per minute. Okay, that's how many kilograms per minute of salt is coming in from one of the inlets. And then I look at the next statement to see what's happening with the second inlet. Brine that contains 0.4 kilograms of salt per liter enters the tank at a rate of 10. Okay, that's also coming in. 0.04 kilograms per liter multiplied by 10 liters per minute. Okay, so that gives me the rate of addition. So that is equal, I mean, I do this arithmetic here, and I get that this is equal to 0.65 kilograms per minute. That's the rate of addition. So then I go for the rate of removal. Okay, we are assuming instantaneous complete mixing, and the tank always has. So these are some of the things to consider. Tank, the volume is not changing. Tank has volume 1,000 liters. Okay, so when I want to know how much salt is leaving the tank, I need to understand what is the concentration of the water exiting the tank, because then I can multiply by how much is exiting, and I will know how much salt is being removed. So the tank has a volume of 1,000 liters. It is filled in the beginning, and we notice we have 5 liters per minute plus 10 liters per minute in, and we have 15 liters per minute out. That is how come I know the volume is staying constant, right? So we have 15 liters per minute coming in, 15 liters per minute going out. So therefore, the volume does not change. So I'm now going to say, okay, that's fine. So now I understand how much salt is coming in. I want to understand how much salt is going out. So I need to know what is the concentration of the salt at time t, okay, inside the tank. Concentration of salt at time t inside the tank. Okay, the concentration is the amount of salt in the tank divided by the volume of the tank. Mass divided by volume. Okay. Maybe I'll just even write that. This is the amount of salt in the tank at time t. And then we are dividing that by the volume of water at time t, which doesn't change. Actually, the volume of the water stays 1,000 liters at all times t. Okay, so the rate of removal is thus. It is y of t divided by 1,000 multiplied by how much water is going out, 15 liters per minute. Units can be really helpful here. This is in fact, let me just expand this out and try to do a nicer job watching the units, because they can really kind of help you to see what's going on. So this is kilograms. That's the amount of salt, volume of the tank in liters. And then I'm multiplying that by 15 liters per minute. Now I'm getting the rate of removal of salt from the tank. This cancels out. The liters cancels out. Liters cancels with liters. And I find out that this here is equal to 3y of t divided by 200 kilograms per minute. So that's my rate of removal. So I have my rate of addition, I have my rate of removal. I plug that back in to the differential equation I am trying to develop. So that was dy by dt equals the rate of addition minus the rate of removal. And then we will recall also that we knew an initial condition, y of 0 equals 0. Look at that. Where are we now? An initial value problem with a separable differential equation. And we are now experts in how to handle this situation. So so now that we've gotten to here, solve for yourself. I'm going to give some direction here and solve it, but stop the video. We have just learned how to solve these things. The hard part of this problem is going from the physical description of what's going on to getting to the initial value problem. Once we've got the initial value problem, we can handily solve it, and then actually we'll be able to tell you how much salt is in the tank at any time t that you choose. So let me put some of these steps down here for solving the initial value problem we've developed, but try it yourself. Way better to do it yourself. Okay, so I'm going to first make a common fraction so I can see how to separate more easily. It's going to be 130 minus 3y over 200. So that's just adding fractions here. And then what I will do is separate, and that will give me the following. dy over 130 minus 3y is equal to dt over 200. And then I integrate both sides, and I see the log function is going to come up here. And so you may be able to do this without substituting on this left-hand integral. You may need to substitute. Any which way, we know how to solve these integrals. And this is going to be minus 1/3 log of 130 minus 3y. And on the right-hand side, that's going to be t over 200 plus a constant. Okay, y of 0 equals 0. That allows me to compute c. That will be, that's going to give me this here. Minus 1/3 the log of 130 is equal to c. That's what the initial condition tells me. Okay, so then I can put that in. Minus 1/3 log of 130 minus 3y is equal to t over 200 minus 1/3 log 130. Okay, looks a bit ugly. I'm going to do some algebra on this, and I'm going to write down a couple of the steps, but now we are, from here on out, we are algebra. So let me just maneuver down a little bit. So before I make one step here, I'm going to pause at the step. So there's some steps missing here. Please complete those yourself. And I'm going to maneuver to here, 130 minus 3y to the 1/3 equals 130 to the 1/3 e to the minus t over 200. Okay. Now I'm looking at this. I'm trying to solve for y if I can. Let's make a nice, make a nicer function possibly, or nicer looking function. Anyways, same function, but just looks nicer. Now of course, as you know, sometimes the absolute value signs can be a real bugbear. You have to be careful with them. But I'm looking at this one, and to make this next step, I'm going to observe that this thing here is never 0. Right? It's an exponential, which is always positive, and 130 to the 1/3 some positive constant. That is never 0. So the left-hand side cannot change sign. Right? Because if it were to go from a positive to a negative, or from a negative to a positive, it would have to go through 0, and that can't happen. So I look over here, and then I observe that this thing is continuous. It's continuous, and I know that y of 0 is equal to 0. And then I could see that when y is just, well, no, I know that y of 0, no, I know that y of 0 is 0, but when y is 0, okay, that's fine. It's not a false statement. But take a look at this. For example, I know that y takes on the value 0 in this problem, right? Because that's my initial condition. And when y is 0, this thing is positive. Positive when y equals 0. Therefore, it's going to be positive all of the time. So I can remove for all values of t. Therefore, I can remove the absolute value signs without putting in a negative sign. Caution and danger, right, on these things. So I'm going to remove the absolute value signs, and I'm going to cube both sides. All right, and then that I can now easily solve for y. So there's a little bit more algebra, but it's a little bit more straightforward. So more algebra, and that allows me to write an expression. The amount of salt in the tank at a given time t is 130 over 3 times 1 minus e to the minus 3t over 200. There it is. And then we had some other question. I think we had a y of 60 minutes. So we can quickly figure out what that is by plugging in 60 for t. Why don't you try that out? You'll get 25.7 kilograms approximately. It's not an exact number. And then I think a little bit more interesting question is, what is the limit as t goes to infinity? So this is like, what is the steady state solution? After a long period of time goes by, how much salt will be in the tank? And it'll sort of be the unchanging steady state near the end. And you could take that limit as t goes to infinity of this guy here, 130 over 3 times 1 minus e to the minus 3t over 200. As t gets very, very large, this thing goes to 0. So this limit is 130 over 3, which is approximately 43.3 kilograms. So you have this tank situation sitting here like that. You've got one concentration running in here. You've got another concentration running in here. You've got mixed water running out here. And this process goes for a really long period of time. And then in the limit that you would have 43.3 kilograms of salt in the tank. That is a classic mixing problem. So you can have lots of flavors of this, one pipe coming in, 3 pipes coming in, 2 pipes going out, whatever. You can change it all around, but basically they all fit this kind of a model, the mixing problem. Okay, that's it for today. I'm going to be back, and we are going to look at some more interesting topics. Thank you.